Then from there, we looked a little bit at the applications of solving these differential equations. Well, the first application is to find and describe families of orthogonal trajectories of or functions. So, so we did one example. We're going to finish this topic with another example. So they're asking us to find the orthogonal trajectories of a family of curves of the form y equals to kx. And if we observe this family of functions y equals kx, so this is a family of linear functions. Number one, that's because the variables are raised to the first power, and well, that k for different values would represent the slopes of those linear equations, right? So let's see. So k, again, it's just an arbitrary constant that describes the slope in this case. Okay, so let's get started by taking the derivative of the function. So the derivative of y equals kx, that's just going to be dy dx equals k times the derivative of x, which is just 1, that's just k. So that's it for the derivative, and in this case, well, all we have to do, because we want to go back and find the family of orthogonal trajectories, that's going to be, in terms of x and y, not in terms of k. So what we have to do here is solve for k in terms of y and x. So that's y over x. And this quantity, we're going to plug it in here to come up with another differential equation that contains x's and y. So that's going to be dy dx equals y over x, all right? And again, this derivative right here represents the slopes of the family of lines, the ones that we have described in the original problem. Well, so we need to find the family of orthogonal trajectories. So what are we going to do? We're going to do the orthogonalization process, or orthogonalize. And well, that remains dy dx equals, so recall that to find the orthogonal family or the perpendicular family, well, so recall that stems from the fact that we are finding the slope of the normal line or the perpendicular line, and to get the slope of the perpendicular line we need to do two things to the slope. So what are those two things that we need to do? Negative and reciprocal. So change the sign and find the reciprocal of this. That is, in this case, well, we have a new differential equation to solve, and this one is separable. It's nicely separable. That's dy times y minus x dx. And we can integrate both sides. This is really easy to integrate, just general power rule. The integral of y dy, that's y squared over 2, and minus x squared over 2 plus c. Recall that we only add the plus c on the right hand side of the equation. We add only one constant that accounts for both sides by absorption. So let's have all the variables on the right hand side. That's x squared over 2 plus y squared over 2 equals to c. And if we further simplify this by multiplying both sides by 2, well, the 2's cancel here, leaving us with x squared plus y squared equals to, what is c times 2 again? Just another constant c. Now, what is this family of functions representing? X squared plus y squared equals a number. It's a circle, right? Depending on the value of c, 9, 16, 64, 625, your favorite number. So, circles. And in other words, actually, this is going to take us back to the example, to the image that we have when we first introduced the topic, right? So isn't it the family of lines orthogonal to a family of lines, and vice versa, a family of lines is orthogonal to a family of circles? Well, we had it only as a picture to describe what it is, but now we did this, or we, in a way, we proved this analytically. All right, let's go to another topic. Mixing problems, some chemistry applications. Well, it's not even chemistry, it's just a mixture, so I don't think this undergoes or implies, this doesn't imply undergoing some chemical changes at all. So this is the picture. So we have, I don't know, a big container with a solution inside, and that is a solute and a solvent. You know, those are the two elements that comprise the solution. And we have some other thing coming into the tank to make a mixture, and well, once we make the mixture, that mixture comes out of the tank. Now, so we will be interested in a particular solid, for example, salt or sugar or alcohol. If we make a mixture of beers, in fact, that's one of the examples, to mix beers and come up with a mixture of beers with a different alcohol percent. You'll see how that's going to work. And well, so here's the thing. The thing is that this amount varies between the rate in and the rate out. And the reason why it's in this order, rate in as a positive sign and rate out as a negative, is because rate in, well, an amount is feeding the tank or the vat, whatever that is, and making or increasing that rate, increasing that amount of solid, and whatever comes out of the tank, that's going to reduce the amount of solid in our system. And well, we further describe this rate in as the flow rate in, which is going to be given the initial concentration, and flow out rate and concentration in which goes out. All right. So I think an example would be better to see this in action, see how it works. So what do we have? A tank that contains 1,000 liters of brine with 15 kilograms of dissolved salt. Pure water enters the tank at a rate of 10 liters per minute, and then the solution is kept thoroughly mixed and drains at the same rate. So number one, let's highlight some pieces of information here. So a tank contains 15 kilograms initially. Okay, this is going to be important information, and drains at the same rate that it comes in. All right. So let's draw a picture. Let's see what we have. So we have this tank. We have this tank. We have something coming in, something coming out. So what comes in? So, well, initially we have 15 kilograms of salt inside of the tank. And well, what's coming in? They're telling us that pure water is entering the tank. That is just water at a rate of 10 liters per minute. Right? What's coming out? So once the mixture is taking place inside of the tank, what are we going to get? We are going to get a mixture of water and salt. And that comes out at the same rate as it comes in, which is 10 liters per minute. So that's all the information that we have, and that's actually more than enough information to solve our problem. So number one, let's write down our differential equation, dA dt, which is rate in minus rate out, which is further flow in rate, times concentration in minus flow out times concentration out. All right. So let's plug in some numbers. Everything is given actually. All right. So dA dt will be the flowing rate. So what's the rate at which water comes in? It's a 10, right? I'm just going to write the number 10. No need to write the units. We can worry about the units until the very end when we handle numerical answers in our calculation, if any. Now the question here, this could be a little tricky. What's the concentration in? 0, because what comes in? Only water, and in this case we care about the amount of salt, not the amount of water. So for this reason, that's going to be 0. Minus flow out rate. Well, they're telling us that the mixture is coming out at the same rate it comes in, that is 10 liters per minute. Now, what about the concentration out? That's a good question. So,
per 1,000.
Something per 1,000, right? I mean, we don't know because, well, so initially we have 15 kilograms of salt inside of the tank. Water will come in, and then at the same time the mixture, water and salt, will come out. That means that this amount of salt is going to vary with time, right? That means, well, in this case as a concentration, and in this case let's consider the simplest case of concentration. Recall that we can express concentration in many different ways, by percent volume, percent mass, or in the chemical units like molar, normal, etc. You know, you will convert this amount of salt into moles, divide by the total volume to get the molarity. But in this case, well, we're not going to go into that direction, so we're just going to say whatever amount divided by the total volume. Let's go the simpler way. All right. So, well, the first term is going to get zeroed out on the right hand side, and this will give us, okay, 10 over 1,000. That's going to give us dA dt minus 1 over 100 A. So that's the differential equation we need to solve. Question?
What's the A over 1,000?
The 1,000, because that's the total volume of the tank. And the A, well, it's just we call it A because that amount of salt is going to vary over time. So if, for example, during the first few minutes, let's say 1 liter manages to get into the tank, well, some concentration or some mixture is going to come out, and the amount of salt is going to be less than the initial. So that's why it's the variable this time. All right. So let's see, and so let's solve the differential equation. dA over A equals negative 1 over 100 dt, and we can solve this by integrating both sides. That's simply ln of A equals negative 1 over 100 t plus c. But recall that we only add the plus c on the right hand side of the equation, not on the left hand side. And notice something else here. Notice I didn't add the absolute value bars for the quantity A, because in this case we are dealing with only positive amounts of solute. In this case, would it make sense to have like negative 15 kilograms or negative 5 kilograms of solid? Well, so it doesn't make sense. So for physical context, in this case, we can just get rid of those absolute value bars. All right, so let's solve the differential equation, and well, actually, let's find the value of C. Well, to find the value of C, number one, let's call this our general solution. All right. So we need an initial condition to get that value of C. So what would that initial condition be? Well, they're giving us an information that initially we have we have 15 kilograms of salt. So we're going to use that piece of information, which is, this is the initial amount before water comes in, with A of 0 equals to 15. That is, when t equals to 0, A equals to 15. So we can plug in these values in the general solution and find the value of c. So that's ln of 15 equals to -1/100 t plus c, where in this case A equals to 15, 0. This term gets zeroed out, and in this case c equals to ln of 15. Right. So we may go about finding the particular solution to the equation, and well, let's refer to this. Ln of A equals to -1/100 t plus c, which in this case is ln of 15. And so now our goal is to get one single expression that depends, a single expression of A that depends on t. So we can solve for A by exponentiating both sides. However, be careful on the right hand side. Recall that this exponentiation affects both terms. And well, on the one hand, we will cancel the ln with the exponential, and on the other hand, so let me continue here. So this is A equals to e to the negative t over 100 times e to the ln of 15. How is this going? Well, this is just basic properties of exponentials. Right?
It says ln 5 over there.
Oh, ln of 15, right? Yeah. Thank you. And we can cancel out ln of with the exponential, and this will be 15 e to the negative t over 100. So that's the mathematical model that will help us find the amount of salt after any time t. Okay. So guys, those of you that are taking pictures of what I'm doing, please stop doing it. Everything gets recorded and posted on Canvas. Okay. So that's the model. That's the model, and well, in this case, I don't think they're asking us anything else besides. So they're just asking us how much salt is in the tank after 10 minutes. That is, they're just asking us for an expression in terms of t to find that amount. So for example, if you want to know how much salt is after 15 minutes, just plug in a 15 for t. If you want to know how much salt is after 45 minutes, after 75 minutes, just plug in your favorite amount of t. Alright? Let's do another example. Example number 8. So what do we have? We have a vat with 500 gallons of beer that contains 4%. Yes? So we plug in an initial condition, and in this case the initial condition comes from the fact that initially we had 15 kilograms of because, well, before water comes in, all right, before water comes in, that's what we have. You know, it's the amount of the solid that we want to know about at the very beginning, before the mixer comes in. All right. For the second example, we have a vat with 500 gallons of beer that contains 4% alcohol by volume, and well, this is what's going to happen. Beer with 7% alcohol is pumped into the vat at a rate of 5 gallons per minute, and the mixer is pumped out at the same rate. There's a couple of questions here. Number one, they're asking for an expression. Well, we need to find an expression to find our amount at any particular time, but they're asking us for the amount of alcohol after 1 hour, and also the percentage of alcohol after 1 hour. All right. So number one, let's draw a picture here. So we have the tank. And well, what do we have for this situation? What's coming in? So we have beer that is 7% alcohol coming in, which means, well, 0.07 in decimal form. Recall that we don't use percentages in our formulas. We use decimals. Well, in one situation we're going to use the percent anyway, but I'll explain why. And it's coming into the vat at a rate of 5 gallons per minute. Right? Now, what do we have inside of the container? We have beer that is 4% alcohol, which is the same as 0.04 in decimal form. All right? So, what's coming out? Some mixture, well, depending on the amount of 7% alcohol beer that is coming into the tank. Depending on the time, we're going to get whatever mixture, whatever amount of alcohol. But the thing here is, it comes out at 5 gallons per minute. All right? So that's all the information that we have. That's all the information that we need, in fact. All right? So let's write down an equation, set up a differential equation to solve. And so that's going to be the flowing rate times concentration in flow out rate times concentration out. So let's put all the information into the equation. So number one, flow-in rate. They're telling us the rate at which the 7% beer is coming in. It's 5 gallons per minute. Now the question here is, what's the concentration in? It's 7%. 7%, which is 0.07. And see the difference between the previous problem. In the previous problem, we only had water coming in without anything, without any solute within. This time we have water. Well, that's what the beer, water plus other things, you know, the other components. But in this case, we care about the amount of alcohol, which is 0.07, minus flow out rate, which is the same rate of 5. And well, the concentration at which it comes out. But again, when we mix these two beers inside of the container, depending on the time, whatever comes out, it's going to be different based on the amount that already came out versus the amounts that are already that were already coming in. So in this case, this varies. This is our variable, and divide by 500 in this case, which is the total volume, right? Okay. So that's the differential equation. Let's simplify a little bit. That's going to be dA dt equals 5.0 times 0.07, that's 0.35, minus 5 over 500, that's going to be, well, 1 over 100, or 0.01, multiplying A. So let's solve this differential equation. So let's separate the variables. Let's have the t's on the right hand side and the a's on the left hand side. dA equals 0.35 minus 0.01a times dt, and isolating dt, well, we can divide both sides by this 0.35 minus 0.01, and that dt. So now that we isolated the variables, that we separated the variables rather, we can go about the integration to get the original function. All right. So well, the right hand side of the equation, it's just the integral of dt, and that's simply t. However, the left hand side will require a baby u substitution, and I'm going to set up that u substitution here. That's u equals to 0.35 minus 0.01a, and du equals negative 0.01 dA. That means dA equals negative 1 over 0.01 du. So let's go about the substitution. So that's the integral negative 1 over 0.01 du over u, and well, the integral of dt, it's simply t plus c. Recall that we add the plus c only on the right hand side of the equation. Let's clean up the integral on the left hand side first, so we can easily see how we're going to integrate this one. So that's a negative 1 over 0.01 du over u equals t plus c. And well, du over u, what is that integral equal to? Natural log. 0.01 ln of u, well, absolute value for now, t plus c. But once we substitute the u back in, that could be parentheses, because again, in this case, we're only looking at positive values of a, so don't need to care about those absolute values. 0.35 minus 0.01a equals t plus c. So let's keep solving the equation. So we want to get an expression for a in terms of t. So number one, I will multiply both sides by negative 0.01 and cancel this. That's ln of 0.35 minus 0.01a equals, well, if we distribute the negative 0.01 over the t, that's going to give us negative 0.01 t. However, what happens when we distribute the negative 0.01 with the c? It's just another constant, right? Okay, give me 1 second. Yes. Okay, let me know when you're ready. Are you ready? Okay, thank you. All right, so e, let's exponentiate both sides. That's going to be 0.35 minus 0.01a equals, again, by laws of exponents, e to the negative 0.01 t times e to the c. But again, what's going to happen here with the e to the c? What's e to the c? Just another c, right? So that's a c e to the negative 0.01 t, and that's 0.35 minus 0.01a. Let's keep solving for a by, in this case, subtracting both sides the 0.35. That's going to give us negative 0.01a equals c e to the negative 0.01 t minus 0.35. And dividing both sides by negative 0.01, check this out. Check what's going to happen here. A few things. Negative 0.01, negative 0.01, negative 0.01. So number one, these are going to get canceled, of course. But what happens with a c divided by negative 0.01? Just remains a c, and in this case, well, whatever comes out of dividing these two numbers, all right? Which is going to be 35. So I'm going to write down the solution to that part. That's going to be a equals to negative, well, or actually 35 plus c e to the negative 0.01 t. So that's the general solution. And so for the general solution, now we need an initial condition to get that value of c. However, the way we're going to get the initial condition is going to be a little tricky this time, because it's not going to be as simple as like the previous example, in which initially we knew the amount of the solute, in this case the amount of salt. In this case, the information that we have is that information about the percent alcohol in the inside of the tank. Well, so number one, this is the general solution. Okay, and well, so that's a general solution. So we need to know the initial amount of alcohol in the vat. All right, we don't know the amount, we know the percent, which is different. And to get the amount, well, so we need to think about chemistry again, because well, we're given the information as a percent. And recall that there's many ways to express the concentration of a solute in a solution. Well, we can express, well, in this case, they're clearly telling us that it's a percent per volume. It could be percent per mass, or it could be the molarity. If we convert that amount into moles, divide by the total volume, well, that's going to give us the molar concentration. And then, well, so in this case, we will use the percent per volume. So, question?
We have 500 gallons in the bag, 4% alcohol. So why isn't it just 4% and 500?
That's what we're going to do, but we need to express that into the corresponding system of units. So, for example, we know from chemistry that the percent volume is the volume of the solute divided by the total volume, and multiply that by 100%, right? Again, let me label this. So that's the volume of the solute, and that's the total volume. All right? We know that the percent of the solution is 4%. And we know that the volume of the solute is the unknown, and then we know that the total volume is 500 liters. That times 100%. We can actually get rid of the percent symbol. All right. So let's solve for Vs in this case. So that's 2,000 equals 100 Vs, and Vs, the concentration of the solute, will be 20. All right. This means that initially we have 20 liters of alcohol in a solution, or in a 500 liter, or it's not liters, it's gallons, right? In a 500 gallon solution. So now that we figured out the amount, the exact amount of alcohol, we can call this an initial condition, which is A of 0 equals to 20. Right? And that's the condition that we will substitute in our solution to the differential equation. So we're going to go back to where we said. Right here to this equation, we're going to plug in A equals to 20 and T equals to 0 to find the value of C. So in other words, 20 equals, what's that? 35 plus C e to the negative 0.01 T, which in this case is 0. So that's 20 equals to 35. And well, e to the negative 0.01 times 0, well, negative 0.01 times 0 is 0. E to the 0 equals to 1. 1 times c is just c, and then in this case c equals to negative 15. So this means that our particular solution would be a equals 35 e to the negative 35 minus 15 e to the negative 0.01 t. So that's the expression that will determine the amount of alcohol for the beer that used to be 4% alcohol at different times. So you plug in different values of t, you will find a different concentrate or different amount, not the concentration, just the amount. You will get different amounts of alcohol. Now, let's answer part A. What is the amount of alcohol after 1 hour? So what do we need to do to figure that out? Any ideas? What do we plug in? 160. Be careful with the units, because notice everything, all these rates were given in gallons per minute. So if they're asking us for 1 hour, well, then we need to evaluate A at 60, because this was designed in minutes. Times 60, all right? And after simplifying this madness using a graphing calculator or whatever, that's A of 60 equals to 26.77 gallons. All right? So that's the amount of alcohol inside of the vat, mixing the two beers together. So we get 26.77. So it's actually getting more concentrated than it was. And that should make sense. Why? Because check what we had inside of the vat. It was a 4% alcohol. What's coming in? A beer that is higher in degrees of alcohol. So we would expect to get a higher concentration of beer in this case. All right. So now to answer part B, what is the percentage of alcohol after 1 hour? So what we're going to do is divide the volume of the solute, which is 26.77, divided by the total volume of 500 gallons times 100%, because we want to express this as a percentage, and simplifying this should give us 5.35. All right. So if for whatever reason you in the future you get into the beer business, well, a mathematical model that helps us manage these mixers of beers. Let's say you have different beers in your menu. You have this beer that is 4% and this beer that is 7%. Well, so in this case you might want to obtain a new beer, a third beer, that is higher in concentration. So let's say you feel like, oh, I want to obtain something more concentrated, so something in between the 4% alcohol and something between the 4% and the 7%. So you design this experiment, and well, you find out that after an hour you will be obtaining a beer that is 5.35%, and well, that's something in the middle between 5 and 7% alcohol. All right. You can apply this to wine again. I mean, same mathematical model, same idea. Right? So we're done with this section. Let's touch base with section 9.4 very briefly. Models of population growth. We're going to do the derivation of one of the equations that you have seen before back in pre-calculus, college algebra, whatever, or intermediate algebra. So the law of natural growth. So this law is described as the rate of change of the population with respect to time based on its population size. So that is, the population changes with respect to time. It's proportional to its size, right? And in this case, well, again, this one is going to be a very baby model, because a lot of things are not taken into consideration, such as the limitations the community has, or any carrying capacity, limited supplies. I mean, of course, supplies are not unlimited. Otherwise, if supplies were unlimited, well, we can use this population growth, and you will see how. So, and well, the initial condition for the situation is that initially we will have P sub 0, which is the initial population of the community. So let's solve this differential equation by separation of variables. So that's going to be, well, dP equals Kp dt, and then dP over P equals K dt. All right? So, if we integrate both sides, this should be ln of P. And again, I'm not going to write this absolute value bars. Again, that's because, well, we're looking at positive amounts of population. In this case, there's no such thing as negative amount of people, you know? And that's KT plus C. So let's exponentiate both sides to get P by itself. Again, recall that the exponentiation affects both terms on the right-hand side. So, let's see. So that's P equals to e to the KT times e to the C. In this case, well, again, we're going to do the same. E to the C, e to some constant is just another constant by absorption, e to the KT. And so that's the general solution for now. Alright, to get the particular solution, we're going to use our initial condition. This initial condition is essentially telling us that when t equals to 0, the population is the initial population, you know, the population at the beginning when we start making the experiment, the study, you know. So let's just plug in where it corresponds. So we will plug in t equals to 0 and P equals to P initial based on the initial condition, that is P initial equals C e to the K times 0. But again, 0 times K is just 0, and e to the 0 is 1. 1 times C is C equals to P initial. So that's the constant of integration, and incorporating this into our general equation, or a general solution, that's P initial e to the KT. And well, I think you have seen this model before a number of times in intermediate algebra, pre-calculus. However, back in the day, they just told you use this model. Don't ask where is it coming from, because well, and now here's the reason why they didn't tell you where it was coming from, because you needed to know a little bit of integration, what else, differential equations, in order to go from the definition of the variation of the population, which is directly proportional to its size. Well, that gives rise to a differential equation. You didn't have the tools back then. So now that we have these tools, we can see where is this model coming from. And again, this K, depending on its sign, that means if K is positive, this model will represent growth. But otherwise, if this model has a negative K, that will represent a decay. All right, like those problems in radioactive decay from pre-calculus or population growth, depending on the sign.